All right, welcome back. We're in 6.1, which is systems of equations in two variables. So we'll start that, and oh, here we go. We're starting. So we've dealt with systems of, well, not even systems, just equations, linear equations with one variable. We're going to start seeing, though, that sometimes we have systems which will have two equations. So examples of these, something like 3x plus 2y equals 10. And another equation, say whatever, 5x minus 8y equals 27, right? It's two equations that have two variables. Or, I mean, there's more. You can have three equations, three variables. But however many variables you have is how many equations you need in order to solve this, right? So if I want to see if a, let's write this, is the point 2, 3 a solution to the system, this system, right? I can plug these values in. 2, 3 is an ordered pair. It's an ordered pair because I need an x and a y. And I'm going to take my x value and plug it into each of the x's, and then my y value and put it into each of the y values, right? If it creates a true statement on both equations, then it's a solution to the system. If it doesn't, then it is not, right? So let's take a look, and I'm going to try the first equation. So 3 times 2 plus 2 times 3 should equal 10. 3 times 2 is 6. 2 times 3 is also 6. Does this equal 10? No, it doesn't. Right? So I can stop here. Once it fails one of the equations, it's not a solution. So this is not a solution. So I don't have to keep going. I already know it's failed. Right? Is 3, negative 1 a solution to the equation, or the system of equations, 2x plus 3y equals 3, and 3x minus y equals 10. Right? Well, we try it, right? Try this guy, put in the x value into the x, the y value into the y. That would be 2 times 3 plus 3 times negative 1 should equal 3. This is 6 minus 3 equals 3, and we can see that it does. So it's a solution to the first equation, right? But it has to be a solution to the second one as well in order to be a solution to the system. So let's try the second one. 3 times 3 minus negative 1 should equal 10. 3 times 3 is 9, minus negative 1 is the same as plus 1, and we can see that this solves both. And therefore, the answer here is yes, it's a solution, right? Now we can look at these in a lot of different ways. I might have a system where I'm asked to solve the system. And let's say I have x minus y equals 5 and 2x plus y equals 1. Right? So let me grab a coordinate plane here. That's all right. 1 there. Steal this one. All right. The first way that we would consider is graphically. This thing out of my way. All right. So if I graph both of these lines, let's graph this top one in red, perhaps. I'm going to rewrite this. I'm going to subtract y to the other side and subtract 5 to the other side to give me x minus 5 equals y. Or Similarly, y equals x minus 5. This is easy to graph because it has a intercept of -5 and a slope of 1. So up 1 over 1, right? And it's easy to graph that. Let me throw, don't do that. This, right? And I'm going to use a ruler here because, I mean, I think you've all seen me draw a line, and never have I done anything close to a straight line. But there's my graph of that line. Let's graph the other one in purple. Oh, that's not purple. Purple, right? But if I just subtract 2y on this guy, I get -2x plus 1. That's easy to graph in y equals mx plus b form. So I will. That's got an intercept of 1, a slope of -2, so that is to go down 2 and over 1. So I would say my next point was there. And there's got to be a quicker way to roll this around. I guess not. Looks like that, maybe a little bit more. A little bit more. There. That's good enough. All right. When I draw this line, it's there. And we can see that these two intersect right there, right? And by the look of it, let me maybe zoom in a little bit. Yeah, that's better. They intersect at x equals 2 and x equals -3, it looks like. So my solution would probably be, 2, -3. Right? Let's check that, just double check to make sure that we're right. So I'm going to check in this system. 2, -3. By plugging it into the first equation, right? We'll call that equation 1. If x is 2 minus y, which is -3, that should equal 5. But of course that does. That's 2 plus 3 equals 5. And that, of course, is 5 equals 5. So the first equation checks out. Let's look at equation 2. Equation 2, 2 times x, or 2 times 2, plus y, which is -3. Oops, there's a lot of extra minus there. -3 should equal 5. But 2 times 2 is 4. 5, not 5. I don't know where I got the 5 from. Probably from the equation above it. Should equal 1, right? That is 4 minus 3 equals 1. And that, of course, is true. 1 equals 1. So it's right. We got the right spot. Bam. We're awesome. Look at us. Now, this method has some drawbacks. For example, if I were to graph an equation, graphing has its drawbacks anyway, but if I were to graph an equation that looks like this, let me use a super thin pen maybe. Right? And then I have another equation. Like, oh my gosh, it drives me crazy. That looks maybe like this. Right? And I graph this guy here. And we say, all right, super. My solution is in here where these two cross. Where is that? And it's hard to say because it didn't land on one of these nice little, crosshairs of our beautiful graph paper. Right? It's in the middle of one of those squares. I don't really know exactly how to say that, right? So for example, if my answer maybe, -4.25, right, in the x value, and maybe like 1.5 in the y value, but this is just a guess. It's somewhere in that neighborhood. I'm probably not far off, but I can't say with any certainty that that's my value, right? So this is the downfall of graphing, is if it's not a nice integer value, it's hard to tell what it is on a graph. So this is the least preferred method as far as accuracy goes, but it's all right to kind of eyeball where your answer should be, right? But we would move on to another method called the substitution method. And the substitution method is great for problems that look like this. Excuse me. All right, we have a system. Let's say that we have, in fact, let's use that same one. It's x minus y equals 5 and 2x plus y equals 1. We already know the answer. I forgot it, but it's up there somewhere. The answer is 2, -3, right? So we should end up with this, but the nice part is about substitution is you don't rely on any visual and hoping that you land on those intersections. But for the substitution method, I'm going to pick a variable, and it doesn't really matter which one that you pick. In this case, I'm going to pick that x that I just highlighted, just because it's easy, right? It's easy to solve for, and I'm not going to end up with fractions or decimals or something, but I'm going to pick out one of the variables that's super easy to solve for and solve for it. Okay, I have a highlighter still. So solve one equation for one variable. Right. So again, I chose this x. All I'm going to have to do is add y to both sides, and that gives me x equals 5 plus y or y plus 5. It doesn't matter. And furthermore, it gives me an equivalent system, 2x plus y equals 1, right? Is the other equation still. But this expression, 5 plus y, is now equivalent to x. And so I can replace the x in the other equation with it. So I will. That's the second thing I do, is replace. I don't want to write this by hand. I don't know why. Replace, like typing's any better. Replace the variable in the other equation with the equivalent expression, right? So that is to say, this x right here is going to be replaced with this 5 plus y. So that gives me 2 multiplied by the quantity 5 plus y. Make sure you get your parentheses in there. Still plus y equals 1, right? And if I distribute, that goes through. That gives me 10 plus 2y plus that y still hanging out there equals 1. But now I've only got one variable, right? So I can solve for this. If I combine my 2y and my y, then I have 10 plus 3y equals 1. Subtract 10 from both sides. This becomes 3y equals -9. And divide each side by 3. That gives me y equals -3. Right? And I'm halfway there. That's one of the values. I need to solve for both. So don't stop here and call it good, right? This is one of my values. For the other one, I already know y is equal to -3. So I'm going to take this all the way back up here to probably, typically, that equation where you solve for the other variable, because it's going to be very easy to just plug in y equals -3 into here and solve it. So if I do, this is now x equals 5 plus y, but y is -3. So 5 minus 3, and x is equal to 2. Oh, well, that looks very familiar. There's my other part of my answer. Yoink, right? If I write this as an ordered pair, that is 2, -3. And wouldn't you know it, that was indeed the answer that we got on our last one, right? Okay. So there we are. Not too bad, is it? Yeah. This one is ideal for when you have just kind of an X or a Y hanging out there that's not multiplied by anything, right? But sometimes, and that'll be the downfall, is if you have to do work to solve for that. So for example, we won't work this one, but because it's going to be a horrific answer probably. Right? In this one, it's hard to pick out an X or a Y that you're not going to just fudge up the rest of the work that you're going to have to do, because it doesn't matter which one. Pick one, any one. I want to solve for that X. I'm going to divide by 3. I know this 32 is going to eventually get divided by 3. It's not divisible by 3, so I have a fraction right from the get-go. And I'm going to take that fraction, cram it into the other equation, get a worse fraction. And so this is the downfall, is when you don't have something just nice hanging out there that you can say, hey, it's super easy to solve for that variable by doing very little work, right? When that's the case, we're going to look at another way to solve a system. And that other way is called the elimination or the addition method. All right. So let's take a look at this one. And let's use this equation. So this one is ideal. In fact, if we're being honest, I go to this one first. It's the last one we learn, but it is the catch-all. It'll do everything. And so I go to it first. Sometimes it's a little more work, but it'll do all of them. So if I have a system, let's say I've got 2x plus y equals 2, and x minus y equals 7, right? Just remember, if you will, recall the addition principle, I don't know, principle. At some point, I should probably learn the difference between those two. I don't care. Principal with a PAL is like the leader of an organization. Principle with a PLE is like, I don't know, the set of rules that you go by. So I am inclined to say that it's principle that way, but I think I've read it as PAL in books. I don't know. Who cares? It's the addition principle of addition, right? And we said if A equals B, then if I add C to one side, I simply have to add C to the other side. So A plus C is equal to B plus C, right? Well, we're going to expand on that just a little bit, and we're going to say this. If I have A equals B and I have C equals D, right? So now I have two things that are equal. In this equation, A equals B, I can add C to one side and I can add D to the other side. And because those two are equivalent, it's like adding the same thing to the other side. So that tells me that A plus C is equal to B plus D, right? And that's the key to this, is I'm going to start with an equation. I have another one right here, and I'm going to take the x minus y and add it to the left-hand side of the equation, and take 7 and add it to the right, because they're equal. So I'm just going to add the left hand to the left and the right hand to the right. But if I do this, I can combine like terms. 2x plus another x is 3x. And oh my goodness, what happens here? A positive y and a negative y cancel out, and they're gone, right? And in one step, I've got this down to a very easy equation. Divide by 3, and x is 3. and I'm already halfway home, right? Once I know x is 3, I'm going to take that 3 and plop it into x in one or the other equations. It doesn't matter which one. Pick one and run with it. X is 3. I'm going to plug it into the second equation, so minus y is equal to 7. I can solve for this, subtract 3 from both sides. So I get minus y is equal to 4. Multiply both sides by a -1, and that gives me y equals -4. And I'm done. My ordered pair solution is x was 3, y is -4, so 3, -4. And of course, you can take that, chuck it back into each of the equations, and it should solve both of them. Right? Okay. Now, I'd mentioned the downfall of substitution. I'm going to scroll this up just a little bit here. Was when I had something that looks like this, right? It's hard to get one of those x's or y's isolated, right? So if that is the case, your addition and elimination method can take care of that. Sometimes you have to do a little bit of work to get it there, but let's take a look at this system. Let's say 4x plus 3y equals 11, and negative 5x plus 2y equals 15, right? If I just go straight out and say, oh, I'm just going to add these together, I've got 4x and negative 5x, which ends up with negative x, and then 3y and 2y is 5y, and then 11 and 15 is 26, and that does me no good, because now I just have another equation with 2 variables, and I don't want that. I want 1 by the time I get here. So I'm going to back up, and we're going to talk about what we can do to manipulate this stuff. Right? I'm going to pick the easiest variable. So I'm going to take a look at both numbers in front of my y, a 3 and a 2. And I'm going to ask myself, is that going to be easier to work with or harder to work with than these two numbers right here, the 4 and the 5? And in this case, it's not a huge difference, but let's take the 3 and the 2y, right? Because they're smaller for no other really reason. You might also consider the x's because one of them is negative already. But what I want is the variables on one or the other of my variables to be the same magnitude but opposite sign, right? So that is, I want to manipulate my 3y and my 2y to be a 6y and a negative 6y. How do I do that? Well, I use the multiplication principle of equalities, and I can multiply the top one by 2 while multiplying the bottom one by a negative 3. Right? This will give me a new system of equations, but it's equivalent. Multiplying the top one by 2 turns this into 8x plus 6y equals 22. Multiplying the bottom by negative 3 turns this into a 15x minus 6y equals negative 15. And now if I combine these guys, 15x and 8x, right, it's a little bit large. It's what, 23x? But 6y and negative 6y cancel, and they're gone. Over here, 22 minus 15. Well, that's not going to be pleasant. I mean, it's 7. There we go. Oh, no, it's not. Okay, timeout. I'm going to back up. I see my mistake. If you're watching this on video, you've probably caught it already as well. 15 times negative 3 is not negative 15, right? It is. Ooh, look at that. I can save it with, it's negative 45, right? So the difference here is not 7, but negative 23. Oh, how convenient is that? Because if I divide each side by 23, I get x equals negative 1, right? And I'm halfway there, right? So it was a little work to set it up, but then again, it kind of falls together very nicely. Right? But since x is negative 1, I can take that and plug it into an x value of one of the original equations. It doesn't matter which one. Do it to both. It doesn't matter. You should get the same answer. So I'll pick the, I don't know, the top one, the top original equation in black. So 4 times x, which is negative 1, plus 3 times y equals 11. Or negative 4 plus 3y equals 11. Add 4 to both sides. And I get 3y is 15. And divide each side by 3. And y is 5. So I have negative 1, 5. And that's my ordered pair and the solution to this problem. All right, let's grab. Let's look at this one. There's a couple of things that can happen while you're playing with these. Let's solve x minus 3y equals 1. And negative 2x plus 6y equals 5. So for me, I would probably manipulate the x's because they're very easy to manipulate. If I just multiply the top equation by a positive 2, then I get the equivalent system, 2x minus 6y equals 2, right? In fact, no, that's fine, because I have a negative 2x here and a positive 6y equals 5. If I combine these, though, the x's cancel out, the y's cancel out. That leaves me with a 0 on the left, but on the right-hand side, I have 5 plus 2 is 7. So if this happens, right, my x's have canceled out, my y's have canceled out, and I get a false statement. What does that mean? Well, graphically, it means, in fact, I'm just going to steal this graph from the book because I can. These are 2 parallel lines, right? Where do 2 parallel lines meet? Never. There's no solution here, right? And so that is to say that there is no solution. So if you boil down to a blatantly false statement and your x's and y's disappear on you, there's no solution. And that's it. That's your answer, is no solution. Let's look at this one. 2x plus 3y equals 6, and 4x plus 6y equals 12, right? Once again, I will probably look at the x values here and multiply the top one by a negative 2 to make my x value, the coefficient in front, a negative 4, right? So my system, my equivalent system, is negative 4x minus 6y equals negative 12. And then on the bottom, I haven't changed anything, so I get this. When I try to combine these, nothing, nothing, and nothing. Everything cancels out, and so I get 0 equals 0. But this is true, right? So what does that mean? Well, in this case, these two are the same line, right? And therefore, that's why this boils down to a true statement is you've got this one line, the other line is right on top of it, it's the same line. So we would say that there's infinitely many solutions, right? And so those are the two odd cases. I mean, they're not that odd, but if you have two lines that have the same slope, you've got two options. They're either the same line, in which case all of the points on that line are solutions to the system, or if they are parallel lines but not touching, then they never touch and there's no solutions. Okay, so let's grab this problem here, and we'll work through this one. All right. An airplane flies the 3,000-mile distance from Los Angeles to New York with a tailwind in 5 hours. Takes them 5 hours. The return trip against the wind takes 6 hours. Find the speed of the airplane in still air and the speed of the wind. So in a problem like this, we're talking about distance equals rate times time, right? And I have two trips. I have one with the wind and one against the wind. So I'm going to make a chart here that gathers all of the data that I have. I'm going to have distance, rate, and time. Okay. So I know a couple of things. It's going the 3,000 miles both ways. So the distance is 3,000 in both cases. But when I'm going with the wind, I have two things happening, right? Let me get down here just a little bit. I have this airplane. That's a beautiful airplane. And if it's going with the wind, there's two velocities to take into consideration, right? X will be how fast the airplane goes relative to the air. And then let's just call Y the air, the wind, right? How fast the wind is going. So if I'm traveling with the wind, I'm traveling X miles per hour in what would be considered still air, but that wind is helping me, it's pushing along. So my rate as I travel with the wind is X plus Y. Right? On my return trip, my beautiful airplane now is going this way, but the wind is still going that way, so it's pushing against the wind's trajectory, and therefore the rate as we go against the wind is the rate of the airplane minus the rate of the wind. Right? And then the times, it takes 5 hours if we go with the wind, and 6 hours against the wind. Okay? Knowing all of this data now, I can create two equations. From this equation, distance, which is 3,000, is equal to the rate. The rate is X plus Y, multiplied by time, which is 5. From the other equation, distance, which is still 3,000, equals the rate, which is now X minus Y, multiplied by the time, which is 6. And so if I create, I'm going to scooch over a little here, a system out of this, this becomes, I'm going to just start here on the right-hand side, and it's going to become my left-hand side over here. I'm going to distribute the 5 through, so that becomes 5x plus 5y equals 3,000. Just move that 3,000 to the right. And the same thing over here, but I get 6x minus 6y equals 3,000. All right? And that's my system. I can use the elimination method. I can use the substitution method. And in fact, if I chose to use the substitution method, it's not bad. I can solve for this x really easy because this 3,000 right here and this 5y are all divisible by 5, right? So I can actually, right from the get-go, just like I can multiply everything by a number, I can divide everything by a number, right? And so I'll just write this as an equivalent system before I do anything else. If I divide everything in the first equation by 5, this just gives me x plus y equals 600. And in fact, hey, why not do the same thing here? Take this bottom one and divide it by 6, because, you know, I can. That gives me x minus y equals 500. Right? And now I don't even have to bother with substitution. I'm just going to combine the two. This gives me 2x on the left equals 1100 on the right. And if I divide by 2, then I get x is 550, right? And that's how fast the plane was going, right? How fast is the wind? Well, plug in x into here. That gives me 550 plus y is equal to 600. So if we subtract 550, we can see pretty easily that the wind is 50 miles an hour, or 50 whatever units we're talking about. Miles per hour. All right, so those are not always the easiest to understand the first time around, but play with them. There should be some in your homework. If you get to a point where you don't understand it, look up, again, I can never remember if it's Khan, K-H-A-N or K-A-H-N, but Khan Academy has videos on this as well. I can also do a video if you want me to do a video on another problem like that or other problems, I can do that as well. But if you go to Khan Academy to look it up, just look up, what is it, under something like, I think if you write with and against current problems, right, that's what this I think would be listed as, with or against current. But if not, look up systems of equations, applications of systems of equations. Right. Or if you're just flabbergasted, let me know. I'll do another video just focusing on these if you would like, and post it. But that's it for 6.1. So have a good one. I'll see you guys next something Monday. All right. Take care.